Dear students, today I will be posting my next video on analog electronic circuits, in which we'll see what are closed loop circuits and what is a virtual ground. Okay, so the heading will be closed loop configuration of op-amp and virtual ground. So in this we are going to see closed loop configuration of op-amp, what is virtual ground, why we need virtual ground versus real ground. Okay. So first we'll start with what is closed loop configuration of op-amp. So if you see the concept of closed loop or configuration, okay, if you have a note on it, the utility of op-amp increases considerably if it is used in a closed loop mode. The closed loop configuration of op-amp is possible using feedback. The feedback allows to feed some part of the output back to the input. In linear applications, the op-amp is always used with negative feedback. The feedback helps to control gain, which otherwise drives the op-amp into saturation. Okay. So here, what we have to show is, say for example, if you're having a op-amp circuit, okay, this is minus, this is plus, and here you are having output V naught. This is V1, this is V2. Okay. Now, what you will be having is you will be having a feedback line from output to input. This will be your feedback resistor. Okay. Feedback line, and most of the time that feedback line will be given to a inverting terminal. So it is a negative feedback. Okay. Now, this feedback, what will do is it will reduce the gain of the amplifier circuit of the op-amp circuit as compared to open loop configuration. So in open loop, the gain was infinite. But in closed loop, when you have made it closed, here you are having a feedback and that feedback is making a close. This is, you are making close. This is where the closed concept will come into picture. Okay, so due to this, the gain will be reduced. The output will not cross any saturation level. Okay, the output will not cross any saturation level, and the gain will be reduced. The circuit will be stable and can be used for linear applications. Okay. So here you can see op-amp with negative feedback. Okay, so here you can see this is the input given to the inverting terminal here, minus terminal, and this is the input given to the plus terminal. This is the output taken V naught, and this is the feedback circuit. This is the feedback circuit which is going to give the output back connected to input. Okay, so here you are having a feedback resistor RF. Okay, and this feedback sees that the output does not reaches saturation level, or the waveform at the output does not clip out. Okay, at the compromise of reduction in gain, but that gain also can be controlled by deciding the values of the feedback resistance. Okay, so in this way you can control gain, you can have stability for circuit, and you can use this op-amp for linear applications. Okay. So here on negative feedback, the negative feedback is possible by adding a resistor as shown, is called a feedback resistor. The feedback is said to be negative as the feedback resistor connects the output to the inverting, that is the minus input terminal of op-amp. The gain resulting with feedback is called closed loop gain of the op-amp. Due to the feedback resistance, there is reduction in the gain. The closed loop gain is much less than the open loop gain and is independent of it. Most of the linear circuits use op-amp in a closed loop mode with negative feedback with RF. This is because due to reduced gain, the output is not driven into saturation. This is very important. By reduced gain, the output is not driven into saturation and the circuit behaves in a linear manner. Then we'll go to see what do we mean by virtual ground. Virtual ground means the name only suggests that it is not a real ground. Okay. So as the name indicates, it is virtual, not real ground. For some purpose, we can consider it as equivalent to ground. In op-amps, the term virtual ground means that the voltage at that particular node is almost equal to ground voltage, that is 0 volt. It is not physically connected to ground. This concept is very useful in analysis of op-amp circuits, and it will make a lot of calculations very simple. So to analyze an op-amp circuit, a certain node in the circuit will be taken as ground, and that ground will be not actually connected to ground, but it is taken as ground, and it indicates a virtual ground. Okay. Now what is that virtual ground? See, so here if you see the circuit of op-amp of inverting amplifier, okay, so here you are giving the input V in is there, and then your V in here will be given through R1, and it is going to the inverting terminal. Non-inverting terminal is grounded. This is grounded, and there is a negative feedback which is coming from the output. Now this output will give a negative feedback. Okay, negative feedback because it is going to give it to the inverting terminal. Okay, now this is a inverting amplifier circuit. Okay, now in this case, this point where you are going to give say voltage V1 is grounded, and this point where you are going to give the voltage V2 is considered as virtual ground. Is considered as virtual ground. Now why it is considered as virtual ground, we will see. So our virtual ground, to know, to understand, we can see this circuit. Okay, now in this circuit of inverting amplifier, you can see that this is your input, main input, which has to be inverted at the output. This is the R1 resistor for the inverting terminal, which is going to go as input. Then non-inverting terminal is connected to ground. Let the voltage at non-inverting terminal be V1, and that is equal to 0 because it is connected to ground, and the voltage at inverting terminal, let it be V2. Okay, now V2, why we have taken as ground, that we'll see. Okay, and this is a feedback what is given from input to output, and this is the feedback resistor. This is your output voltage. Okay, now why we are taking here the point as virtual ground and why it is taken as voltage is equal to 0, that we will see. So here in that reasoning, we can see that using infinite voltage gain, we already know that an ideal op-amp will provide infinite voltage gain. Okay. For real op-amps, also the gain will be very high such that we can consider it as infinite for calculation purposes. So here if you take gain as output voltage upon input voltage. So here you are going to take gain as output voltage upon input voltage. Now, as the gain is infinite, that is, this is infinite. Okay. So V out upon V in is equal to infinite, means V in should be equal to 0. V in should be equal to 0. That is this point. So when V in is equal to 0 in this equation of your difference amplification, whatever you have at the output. So V in is equal to V2 minus V1. This is what you are going to get at the input, and this will be amplified at the output. Okay. So V in is equal to V2 minus V1. The actual V in which is going to enter, that is, if you are having this op-amp, okay, this is minus, this is plus. So here you are having your V, okay, in, okay, and here you are having your ground. So this you are going to take it as, okay, V1, and this you are talking as, or this as V2 and this as V1. Okay, now here whatever input you are going to give here, okay, whatever input you are going to give here, that is the difference between the two inputs. So it will be V in is equal to V2 minus V1. Okay, it will be V in is equal to V2 minus V1. Clear? So that is what input is been stated. Now in the above circuit, if V1 is connected to ground, then V1 is equal to 0. Then automatically, when V in is also 0 and V1 is also 0, V2 will also be 0. So here, thus V2 will also be 0. Now in this equation, if you take, Okay, in this equation, if you take here, you have taken V in is equal to V2 minus V1. Okay, so we say that because gain is infinite, V in is 0. Okay, and because V1 is connected to ground, V1 also is 0. Okay, that means automatically V2 will be equal to 0. That is what is given as your virtual ground potential. So here in this circuit, you can see V2 has become 0. So that V2, you can take it as virtual ground. That point, that node, you can take it as virtual ground. Okay, so it is not actually connected to ground, but you can take it as a virtual ground. Clear? Then why we need virtual ground? Okay, so as we have shown that V2 is equal to 0, equivalent circuit is also shown below. V in, V out, and V2, RF and R1 are resistances. Okay, a virtual ground concept is very useful in analysis of op-amp when negative feedback is employed. It will simplify a lot of calculations and derivations. Okay, because it is going to help you to simplify a lot of calculations and derivations. We are going to take that point, okay, which is going to give you the potential 0. We'll take it as virtual ground, and that point will help you to simplify many of your calculations in the op-amp analysis. Then what is the a comparison between virtual ground and real ground? Okay, so our virtual ground, if you see in this our tabular column, virtual ground is a concept that made for easy explanation and calculation, whereas a real ground is a terminal which is physically connected to ground or earth, which acts as a reference point for the entire circuit. Voltage is approximately zero, as we have seen for V2. V2 was approximately equal to zero, okay, at that node, whereas voltage is zero in real ground because it is connected to ground. In a virtual ground, it is not able to sink infinite current. It will not absorb infinite current, whereas real ground will absorb infinite current. So infinite current sink is there in real ground, whereas in a virtual ground, it is not able to sink infinite current. Virtual ground is not electrically connected to ground. That's true, whereas a real ground is electrically connected to ground. Okay. Thank you, students.